Hello Professor, this is Kumudini, and today in this video I will be walking through lab 4 for the DPS912 where I implemented a Linux kernel device driver. The goal of this lab was to complete a partially written driver that simulates a hardware device and then interact with it from user space using standard Linux input-output calls. So I will go ahead and show you my implementation now. So in my lab 4 directory, I have two folders. One is kernel and the other is user. So my kernel folder contains the driver code. So if I go to kernel folder, here I have the driver code that runs inside the Linux kernel. And I have the user folder, user. And inside my user folder, it contains the user space program that talks to it. So now let me go back to kernel and show you what I have in my files. So let's try to look at the header file first. So in my header file, we have two IOCTL commands defined. So the first one is hardware device halt and hardware device resume. These are created using the _IOW macro, which encodes the direction, a magic number, a sequence number, and the data size into a single 32-bit command number. This encoding is important because it helps the kernel identify which driver a command belongs to and prevents conflicts between different drivers. So now let's look at what we have inside my C file. So now let's look at the driver itself. At the top, we have our includes and the two function prototypes I added, one for the read function and one for IOCTL. These prototypes need to come before the file operations struct that references them. The file operations struct that we have is the key connection point between user space and the kernel. It's a table of function pointers. When a user program calls read on our device, the kernel looks up this table and calls our hardware device read function. Same for IOCTL. Notice I used the dot unlocked IOCTL here, not dot IOCTL. The older field was removed in kernel version, so this is the correct one for modern kernels. So the hardware sim, so here's the unlocked IOCTL. The hardware sim function runs as a kernel thread. It initializes the buffer with the letter A and then increments every character once per second, cycling from A to Z. It checks the isHalt flag with each loop. If halt is set, it just sleeps and skips the update. Now the two functions I implemented are here. The hardware device read function. Yeah. So the hardware device read function, its job is to copy the kernel buffer to user space. You cannot use memcopy here because user space and kernel space are separate memory regions. Instead, the kernel provides copy to user, which safely bridges that boundary. It returns 0 on success or the number of bytes it failed to copy. Now I have the hardware IOCTL function implemented. The hardware device for hardware device halt, it sets is halt to true, which causes the simulator thread to stop updating the buffer. For hardware device resume, it sets is halt back to false and the thread resumes updating. Any unknown command returns EIN valid, which is invalid. Now let's look at what we have inside our user directory. So inside my user directory, I have the user_hardware.cpp file. So in this file, the user space program opens dev hardware, then reads the buffer 3 times with 3 seconds gaps, sends the halt IOCTL, reads 3 more times, sends resume, and reads 3 final times before closing the device. Now let's run the kernel terminal. So in my kernel terminal, I go ahead and run this command to build it. Okay, so I run the build.sh, which unloads any existing module, recompiles, and loads the new one. You can see the kernel messages confirming the initialization started register device called the character device registered with a major number and the hardware sim thread create and running. Now let's go to the user directory. So let me open a new tab, and here I am going to go to user directory and run the user hardware. So before that, we need to run the program. So let me clean it and run the make command again, and now run the sudo command. So in the user directory, I compile and run the program. You can see the first 3 reads return advancing values as the thread updates the buffer every second. So after the halt command, the buffer freezes. All 3 reads return the same value. After resume, the buffer starts advancing again. So if we can see here, we have it looking at the kernel log. We can see every call logged, open each read with the buffer contents, the halt IOCTL, and the resume. This matches what the user program printed here, and which answers the second research question, which is they generally match, but they won't always be perfectly in sync because there's no mutex synchronizing the thread's writes and the read function's access to the buffer. So in a production driver, you would protect the shared buffer with a spin lock or mutex. So to summarize, I completed the read function using copy to user to safely transfer kernel data to user space, implemented the IOCTL function to handle halt and resume commands, added the function prototypes and wired everything up in the file operations struct. The driver works correctly as shown by the output. So now let me talk quickly about the challenges I faced. The biggest one was understanding why I can't use memcopy in the kernel. I had to learn about copy to user and how kernel and user space are separate memory regions. The second one was using .unlocked IOCTL instead of .ioctl in the file operation struct, because the old field no longer exists in modern kernels and the IOCTL simply wouldn't call without that fix. So for my self-evaluation, I believe that I completed all the required implementations. The read function works correctly. Both IOCTL commands work and the output matches what the lab expects. I'd give myself a 9 out of 10. Everything works correctly, but ideally the shared buffer should be protected with a mutex to prevent a race condition between the simulator thread and the read function. That's something a production driver would require. So thank you so much for watching my video. This is the end.